A lot of the beginning of Chapter 4 deals with just terms, so make sure you review your notes that are on Blackboard. I just wanted to talk to you a little bit about some of the processes you'll need to know. The first being the idea of solubility rules. You're going to have to know these rules well to apply them when you're writing molecular equations. My suggestion is to practice them as much as you can and to focus on patterns you might see. For example, Group 1A, ammonium, acetate, and nitrate. If those are in any compound, that compound is soluble, and that eliminates a lot of the other rules. And then I would also know things like silver, mercury, and lead tend to make things insoluble. So look at these next two slides and make sure that you've sufficiently studied these rules, because they are on the second test in a pretty significant amount. And also note the things that are generally insoluble, the only exceptions are going to be your Group 1A elements and ammonium. It's a good thing to know. The bulk of this chapter deals with the idea of ionic equations versus molecular equations. The molecular equation is the way you're traditionally writing them, where you write the formulas, you balance charges like we did in the first unit, identifying state of matter. Understand that these AQs mean aqueous, which means soluble, that is dissolved in water, and an S means it is a solid, which means it is insoluble. So if you go back to your solubility rules we talked about a second ago, anything containing nitrate is soluble, so it has an AQ. Anything containing sodium or anything in Group 1A is soluble, so it has an AQ. Silver is generally insoluble unless it's paired with nitrate or acetate. So if it's paired with chloride, it's solid, meaning it is insoluble. And sodium nitrate soluble. So understand that the rules we've been talking about are applied to these equations. When you write an equation in the molecular form, you then break it down into complete ionic equations. And that simply means that everything that is aqueous breaks apart into ions. If there's a subscript in the formula, it becomes a coefficient. And if there is a coefficient in that particular term, then that coefficient distributes to all ions in that term. So note in this one, AgNO3 breaks down into 1Ag plus and 1NO3 negative. NaCl breaks down the same way. Notice that the solid silver chloride stays together, and then your sodium and nitrate compound breaks up because it is aqueous. Once you determine your complete ionic equation, you then have to consider what doesn't really play a role. And those ions that don't really play a role are called spectator ions. They appear in both places as a reactant and product. If you look at this one that we've been working on, your NO3 negative and Na positive appear in the exact same form on both sides. So they're eliminated, and your equation is really the silver ion plus the chloride ion forms silver chloride. In order to determine whether a reaction occurs, it's really asking, is there a product that is a solid? So is there an insoluble product? So you look at this and you write your double replacement products. K2SO4 and MgBr2 would be the two products because it is double replacement, meaning potassium would bond with sulfate, magnesium would bond with bromide. Then you look at those two and decide if they are soluble or insoluble. Both of them are soluble, so there's no reaction. Same thing here. Most of these are going to be double replacement, so I look at the two, I rearrange, and I decide the product identities would be sodium chloride and magnesium hydroxide. You go back to your solubility rules, and you see that magnesium hydroxide is insoluble. So that means you will have an equation. So let's do this one. You write your equation and balance it as though we have done the whole time, and then you begin to break it up into your ions. Note that the 2 coefficient in front of NaOH is now distributed to Na and OH. And the 2 in MgCl2 is now a coefficient just of the term Cl. So you go through and break everything down that's aqueous and leave the solid term together. And then for the net ionic, which is the most important one, you remove all the spectators, and you're left with just 2OH negative plus Mg2 positive yields MgOH2, which is a solid. Again, you can sort of review the next couple of slides to see if you're on the right track. I've put a few other videos on YouTube that I found that other people made that I thought were good enough to use and show some things that would be useful. And you'll see as you do these that there's a lot of patterns to them, and once you do a few, it happens a lot more quickly. So don't get nervous or frustrated with the amount of rules you have to know. As you begin to practice them, they become much easier than you might anticipate. We've been focusing on precipitation reactions, and that's when you have two solutions making a solid. We also have to talk about acid-base reactions and oxidation-reduction reactions. There's a video for each of these two also on YouTube that I found that someone else had made. After you study some, those would be good tools to help you review. When you deal with acids and bases, there's a few little terms in these next couple of slides, so just review them. Make sure you remember them from high school chemistry, and if you don't, you have the terms here. This slide is important. You really need to know your strong acids, and we'll talk about the reactions of them in a little bit, but you just have to know the names. I'll read the names across as they're written. HNO3 is nitric acid, H2SO4 is sulfuric, HClO4 is perchloric acid, HCl is hydrochloric, HBr is hydrobromic, and HI is hydroiodic. Basically, a weak acid is one that doesn't break apart completely. It's a weak electrolyte, and most acids are in fact weak. If it's not a strong acid on that list we just looked at, it's a weak acid. Your common strong bases involve the alkali or alkaline earth metals with hydroxide. These are the most common. Anything else is considered a weak base. And again, it's the same rule, it doesn't dissociate completely. Alright, when you write a neutralization reaction in a net ionic form, you really have to decide if it's a strong acid or base. The key to all of these is that strong acids and bases break apart, weak acids and bases do not. So you write your equation. That is a simple one that you can write in that form, and then you see that it does form a liquid water, and so that is your product. Everything else is aqueous, which means everything else breaks apart. Notice that your weak acid does stay intact, your strong base breaks apart, your water stays intact, and your potassium and sulfite break apart in your products. And then you simply go through and cross out things that are on both sides. In this situation, you don't have as much. The only thing that appears in both product and reactant form is your 2K+. And so your net ionic is just the removal of that 2K. This occurs because H2SO3 is a weak acid. So understand that even if it's an aqueous substance, if it's a weak acid, it does not break apart. When you're writing a net ionic equation, you're looking for a solid product, a liquid product, or a gaseous product. Those are the things that are going to stay intact, and you break up aqueous substances that are not weak acids or weak bases. So if you write your molecular equation, this one's not too awfully bad. You see that your solid stays intact. Hydrochloric acid is a strong acid, so it breaks apart. Copper chloride is aqueous, so it breaks apart. And then your water and your carbon dioxide stay intact because they are pure substances. And you look, and the only terms you can really cancel out are your chloride terms. So your net ionic equation may look a little different than you might anticipate. The last section of this deals with oxidation numbers, and there's a lot of terms with this, and there's a lot. I put a video with some examples because this one has a lot of rules. If you know the rules, it's easy. You just have to practice them. Just for the record on this, a monatomic ion is one that's on the periodic table, and an element is referred to a substance in an uncombined form. As you do these, understand it's really just simple math. In most of these, you're going to know one of the two terms, or two of the three, however many there are, and you solve for the other one. Oxygen is almost always a -2. Chromium is the one that I don't know. So if I have 2 chromiums plus 7 times -2 equaling -2, I can solve for the oxidation number of chromium. It's just like a little math problem where you say 2x plus -14 equals -2 and solve for x. The half reaction part of balancing equations is essential to know. Understand that these processes occur at the same time, just in opposite directions. And these are just some terms that you're going to have to know. The common oxidation reduction reactions will help you, but it's not essential that you know how to identify them just yet. That's something you'll learn later on. What's important that you know for this test is how to balance them using the half reaction method. So basically, you look at a reaction and you match them up based on common elements. So Zn plus Ag plus yields Zn2 plus and Ag. I'm going to break that up into Zn yields Zn2 plus and Ag plus yields Ag. You go through a series of steps that sometimes you'll use them all, sometimes you won't. If there are elements other than oxygen, you balance them with coefficients. If there's oxygen or hydrogen, you have to add waters and hydrogen ions. Once that occurs, then you balance the charges. See, in this one you have Zn, which has nothing up here, so it's a 0, and it's +2, so I have to add 2 negatives to cancel it out. Then I have Ag plus with a negative here to balance those out. Then you have to cancel out your electrons. The important thing is your electrons have to be on both opposite sides, and with the same coefficient. Once that's the case, you can cancel them out and recombine them. This one's probably a better indicator of the things you'll need to know. So you have your reaction, and this goes through the oxidation states, which is really the way you do it, but the fact is you can look at the things that are common to both sides and pair them up. So your Mg yields Mg2 plus and your Fe3 plus yields Fe. Those are the two reactions that are going on. You go through and balance your electrons and then recombine them. You return the spectator ion and you just put it in wherever it was before, and notice that it works out just fine. Going back to this for just a second, I put a video that has some very specific steps, and I'll put a little bit more instruction online. Your book doesn't really give as much as I think it maybe could, so I will take care of that and just give you a little bit of extra practice. The video online helps too. These last couple of formulas are pretty easy. If you run into trouble, let me know. There's all conversions and calculations you've done before. Please feel free to email if you have questions, and I look forward to hearing from you.